Hello, everybody. Hope you're okay. Hope you're not sitting outside. If you can start by sending me a little hi, hello on chat, it'll let me know who's here. That would be nice. Yeah, it's always cool. I'm going to do that every time. Ah, sorry. It's supposed to go to everybody. All right. So let's do this. Okay. So last time we defined the notion of double integral, right? And what we wanted to define is essentially the notion of sign volume, right? And the notation we used is the following. R is a rectangle which is perpendicular to the, parallel to the coordinate axes, right? Something like this. And so we defined this using the Riemann sum, the double sum, taking the limit. Okay. So today what I want to do is to show you how we can actually compute such a thing without going through the limit. The theorem is Fubini's theorem, and it connects what we saw with what we're going to now define, which is the notion of iterated integral. Okay, so let's see what this is about. It's here. There you go. Okay, so iterated integrals. So the ingredients are the same as we had. So we have a function f, which is defined on some rectangle. The rectangle will be, as usual, AB times CD. Okay, so here is a picture. I have my rectangle like this. This is A, this is B, this is C, this is D. Okay, and I have the graph of my function over here. Okay, and what I want to do now is to slice as we did like for partial derivatives, we're going to slice up this graph for fixed values of x and y. So let's start by fixing the value of x between a and b. Okay, so I take some x here, and I look at the function restricted only to that value of x. Okay. Maybe it looks something like this. Okay, so so what I'm going to do is to look at the graph of this new function. So consider the one variable function. So this is a function of y. It depends on y. Right? So g of y will be f of xy. So this is fixed. Okay, so its graph is that slice right there. So I can look at it this way. So it depends on y. This, and this goes from C to D like this. Okay. Now, I can compute the area under the curve, right? So again, in general, you'd have functions which could be negative, so it's always a sign area, but for the discussion, it's easier just to look at this as area. So I'm going to compute the area of this under the curve here, okay? So area, yeah. Under the graph of this new function, the graph of, I called it G, right? So what do I do? That's easy. Integral from C to D of G of y dy, right? Now what is G of y? This is f of xy. X is fixed. Again, I repeat, we just chose a value of x. You look at that slice, and we're computing this area, okay? Now, yep.
I don't really understand why we fixed x. Like,
okay, you'll see in just a sec. So, I mean, the philosophy of this is to try to use what we know.
To do the multiple integral.
We want to use what we know in one variable, okay? Right. So that's why I'm slicing, so I get a one variable problem, and I'm going to play with that to hopefully get the double integral.
Oh, all right, thanks.
In the first graph, should we consider only the line, or should we view it as a 2D slice? I'm looking at the restriction of the function at that value of x. So basically it's a vertical slice, and this is the one that I drew over here. Okay, so I'm interested in that area. So I'm interested in just the area under the graph of f at the value x. All right, good. Okay, so if I do this for this x, I'm going to get a value. And obviously, if I change the value of x, I mean, the graph of f is not necessarily flat. So as I change the value of x, I'm going to give different values, different areas, okay? So that's where I want to go. Okay. So if we vary x, we get possibly different areas, right? So we're going to get different slices. Now, last class, I don't remember who asked the question, but it was a good question. How did we connect what we were doing to the way we saw volumes in Cal 2? Now, this is what I'm doing right now. If you remember, I'm not going to go through the whole argument with limits and approximations, but essentially, if you remember how this worked, intuitively, if you look at all these slices for all the possible values of x, if you add them up, intuitively you should be getting the volume that you want. Okay, so basically that will be Fubini's theorem, but so intuitively that should give us the right thing. Okay, so what I do is this. So if I have different values of x, I'm going to get different values of areas, different slices, different areas. Okay, and so we can define the function a, right? Or what is a of x? It is the integral from c to d, exactly what we computed, of f of xy dy. Okay, so this is exactly what we can. So you fix an x, compute the area when you slice at x. So now if you change the value of x, you get different values, but that gives you a function, right? So the area function depending on the slice at x. Okay, so intuitively, and that's with big quotes here, the volume is the sum of all possible areas of slices. Okay, so this is with big quotes here, but hopefully this makes some sort of sense to you. Okay, so what does it mean to add up these slices? These slices are infinitely thin, so what does it mean to add them up? It means to integrate the function. Okay, so so what we want to do is this. What we call the iterated integral. Okay, so I'm going to integrate. Now x goes from a to b. So I'm going to integrate the function a of x. In other words, adding up all these slices. Okay, and so if you look at what this expression is, this is the integral from a to b of the integral from c to d f of xy dy dx. I just replaced inside, I replaced a of x by the expression. Okay, and again, what is a of x? It's the area of the slice at x. Okay, so these are just two. This is not a double integral. This is first a one variable integral and then a one variable integral of what you get. Okay, so I'm going to do an example. This is not complicated. Okay, so okay, I'm going to do this with a very simple function. Grab some water. Okay. So here's an example. Compute integral 0 to 3, integral 1 to 2, x squared y dy x. Okay? So what does this stand for? Okay, so the way this is the notation. So you have to start with the inside integral. You can't start from the outside. So you must start. Okay, so what is this thing? This is the integral 0 to 3 of, and I'll put some brackets here, integral 1 to 2, x squared y dy dx. And here, x is fixed. Okay, we'll deal with the x after. So the inside integral, that's your slice, area of the slice, okay? So let's just compute that on the side. After a while, I'll just basically do the computation of the inside part, keeping everything, but now I want to do it separately. So here's what I want to do. This is the integral 1 to 2, x squared y dy. Okay, again, x is fixed. So it's just like the same principle as partial derivatives. X is a constant. We could even factor it out, right? Okay, so let's just factor it out. Integral 1 to 2, y dy. Okay, nice and easy integral. This is y squared over 2 between 1 and 2. Okay, and so this is x squared times 2 squared over 2 minus 1 squared over 2. So this is 3/2 x squared. So that's our function a of x, right? So you can imagine you have your surface, you chop at any x of your choice, and you look at the area of that slice of bread, and it's 3/2 x squared. So as you change your x, you get a different value for your area, okay? So, so now it means that this thing, what is it? I've computed the inside function, it's 3/2 x squared. So this is the integral, 0 to 3 of 3/2 x squared, like that. And again, simple integral. So this is 3/2 times x cubed over 3 between 0 and 3. I'm not mentioning it, but I'm using the fundamental theorem, obviously. So this is x cubed over 2 between 0 and 3. So that's 27 over 2. Okay? So if you have something that looks like this, it's an iterated integral. I mean, I'm sort of intuitively telling you that it's the same as the double integral. It'll turn out that it is, but it's a completely different approach to what we want to compute. It turns out it's the same thing. Okay, so let's take a look at what happens if you do it in the other direction. Okay, so I started, if the double integral gives the volume, so what does the triple integral give us? A hypervolume. So the question is, what does a triple integral give us? If you interpret it in exactly the same way, geometrically, we have a function of 3 variables. So its graph lives in R4. So you're looking at a hypervolume, a 4-dimensional volume. But there are other ways of interpreting these things. We probably won't have time to get there, but yes. I don't know if that answers your question. But yeah, okay. All right, so what I want to show you is what happens if you slice in the other direction first. Okay, so we can slice in the y direction first. Okay. So again, I have x, y, I have my rectangle like this. This is A, this is B, this is C, this is D. Now I can choose some y here and look at what happens only above this, and look at this slice here. That, okay, so we can fix some y between C and D, right? And we can look at F restricted to that line, right? So now I'm getting a function of x now, right? Which is, you get a and b like this, and you get this like that. And I'm interested in this area here, okay? So area, again, sine area under graph of this function. Well, I am going to integrate from a to b the restricted function, so it's just f of x, y, but this time y is fixed. You choose some value of y, you fix it, it's a constant, you get a function of x, and you can integrate this function, okay? Now you can do this for any possible choice of y between c and d, okay? You will get different areas. So it's the same principle as before, but we're just doing it in the other direction, okay? So you can do this for any value of y between c and d, okay? And so we're going to get possibly different values depending on the function f, okay? But for each y, I get some new value, which I'll call, it's a b of y, okay? So we get a function b of y. What is it? It's the area under f when you slice at y, okay? So this is area of slice at y, okay? And what I'd like to do is to add up these slices. So I'm going to take all possible values of y between c and d, add them up. What does it mean? It means integrate, right? So add up. So you get the integral from c to d, integral a to b, f of x, y, dx, dy. Okay? So the inside part, you see that the inside part is b of y. So this is integral c to d, d of y, dy. Okay? So it's exactly the same principle, just we're doing it in a different order. Okay? Now, if you remember for partial derivatives, we obviously got very different things. But in this case, if our intuition is correct, if the function is nice enough, we should be getting the same thing. So let's just check with our example that we had earlier. Okay, so I'm going to take the following. Iterated integral to compute integral 1 to 2, integral 0 to 3, x squared y dx dy, okay? So you see essentially what I'm doing is my function f of xy is x squared y, and the first example was slicing the way I presented the first time, now I'm doing it the other way, okay? Again, always start on the inside, okay? Okay, so I'm just going to copy this, move on here. Okay. So let's look at the inside part. It's the integral 0 to 3 x squared y dx. Okay, so this means that y is fixed. It's a constant, right? So I could factor it out. I'll just leave it there. So I'm integrating with respect to x. So this is x cubed over 3y between 0 and 3. And so this is 27 over 3y minus 0. So this is 9y. Okay? That's the inside part. So it means that my iterated integral is the integral 1 to 2 of 9y dy. Okay? Now that's an easy integral. This is 9y squared over 2 between 1 and 2. So this is 9 halves times 4 minus 9 halves times 1, which is 27 over 2. Same value. Okay. So, again, that confirms sort of our intuition that you should be getting the same thing. Oh, yes, no matter. And so our main theorem here is the following, which says, yes, the intuition is correct, provided the function f satisfies some good conditions. Okay. So here it is, the Fubini's theorem. Which says that the double integral that we defined last time is equal to the iterated integral in both directions. So all these three things are exactly the same. Okay. Now, here are the hypotheses. Okay, so if f is integrable on the rectangle AB times CD, and I'm going to add a star here because we need some extra conditions, which I'm not going to talk about directly, okay, but they are there, okay. Then Fubini's theorem says that the double integral over R, the rectangle, so that's what we defined on Monday. This is the same as the iterated integral, so a to b, c to d, f of xy. Now, you have to be extremely careful, and I'll talk about that when I do more examples. But the dx, dy, you just can't write them in any order you want. You have to change the limits of integration accordingly. So here, a and b are the x values, right? So that means that the dx should be the last, okay? So this is important. Because if you flip only two of them, you're not going to get the right thing, okay? So this is the same as the integral c to d, integral a to b, f of xy, dx, dy. Okay? So again, Fubini's theorem says, if f satisfies certain conditions, and I'll talk about that in just a second, then the double integral that we defined is the same as the iterated integrals both directions. Okay? Okay, so some comment, I'm not going to prove that, but some comments, some notes on this. Okay, the first thing I like to say this because too many people think that all the math that we're doing was done like 300 years ago. Fubini's theorem is from 1907. Okay, so it's not that old. Now, the version that we're doing is actually older than that. It's from the 19th century. what's called the real Fubini's theorem is for the Lebesgue integral, which is more general. So, but anyway. But that's just a historical fact. The second thing about star. So this is a technical requirement on the slice functions, which I'm not going to state because it's just way too technical and not interesting. The only thing you need to know is the following, okay? So all we need to know about this is the following, okay? Is that, and here I want to take a sip of water. And change slides. So, okay. So, all you need to know is the following. So, the technical requirements. So, Fubini's theorem Fubini's theorem's hypotheses, so what are requirements, are satisfied as long as, okay, so here's the only thing we need to know is F is continuous on the rectangle, but that's too strong, okay? Because you'll see in the next class, we're going to try to integrate over more general regions and rectangles. So we need to be able to slacken our hypotheses here, and here's the way we're going to do it. So F is continuous on the rectangle, except on a set of points of measure 0. Okay, so what does that mean? So a set of points, a set S in the plane, has measure 0 if. So intuitively, it means it has 0 area, okay? But formally, what does it mean? It's that you can cover it by rectangles of arbitrarily small area, total area. You can use an infinite amount of rectangles as long as the total area of the rectangles is arbitrarily small. So how do I state that? So if for every real number, which we'll call epsilon, S can be covered. I'm going to give you examples. You'll see it's kind of cute, not so difficult to understand. So if every epsilon greater than 0, S can be covered by rectangles with total area less than epsilon. Okay, so I'm going to show you, so intuitively what it means, we're in trouble. S has area 0. Okay, here are some examples. A bunch of points, separated points, right? Finitely many points. That's an example. A smooth curve, although that's intuitively clear, but not so easy to prove. Let me show you what I mean by this measure zero thing, this is, so here's, okay, so here's an example with a point. I want to cover the point with rectangles which have arbitrarily small area. Hopefully you can see how this goes. So you give me an epsilon, let's say 1/10. Can you find a rectangle of area 1/10 that contains that point? Yes, right? So you take a point and you just take a rectangle around it, and you can make these rectangles as small as you wish, right? So we can make a rectangle as small as we want. Let's do a segment, okay? I'm going to switch slides. So let's say I give you a line segment like this. So the game is to find rectangles that will cover this segment, but these rectangles can have arbitrarily small area. Well, if you make them really, really thin, right? So fix any small number, 1/2, 1/10, 1/1000th, you can take a rectangle, right? That will contain the segment, you make it thin enough to have area less than epsilon. Hopefully that makes sense, right? So suppose the segment has length 1, take rectangle 1 equals its width, and epsilon equals its height. And I'm going to leave you with an exercise which is a bit trickier, but think about it. This is more for fun, but show that the x-axis has measure 0. So you have to be able to cover an infinite line, a line of infinite length, right, with rectangles whose total area is, let's say, 1/2 or 1/10 or 1/100. Can you do that? So there's a trick that you might know from Cal 2 that you can use to maybe do that. Okay, so this is tricky. Okay. Now, my iPad is going to die if I don't do something, so I'm just going to pause my recording and just try something. And if it doesn't work, well, okay, let me just try. So that's not going to work. Let's try it. Oh, yes. Can you see this? Can you see it?
Yes.
All right, good. Okay, well, hopefully this will work. Okay, so that's sort of a side issue, okay? So just keep in mind that if we have a smooth curve and the function, so just, okay, so recap. We'll use that next time. If f is continuous on the rectangle, except say, on a smooth curve, then Fubini's theorem will work. Okay, so we will be able to use Fubini's theorem even if our function is discontinuous on the curve, and that'll be really important for us next time. Okay, but for now, let's just look at rectangles. I'm going to do just a couple of examples, and then I'll stop. Okay, so this will be important next lecture. Okay. But for now, what I want to do is just look at rectangles. Did it die? No, it's okay. So let's just see how this goes. Okay, so we're asked to compute the double integral over r of x minus 3y squared dA.
Sir,
Yep.
just to mention that you're no longer.
Ah, thank you. Yes. Did I actually stop my recording? No, I didn't. Okay, good. But thanks for reminding me. Yes. Okay. So I didn't stop the recording, which is good. Okay, great. Thanks. Okay. So, okay, where the rectangle is 0, 2 times 1, 2. Okay? So this function is continuous everywhere, so we can apply Fubini's theorem, right? So we can apply Fubini, no problem. So it means that this can be computed with iterated integrals, right? So this double integral, this nasty limit of a double sum, is actually the same as either way, right? So, but you have to be careful how you write it. So 0, 2 are the x values, and 1, 2 are the y values. So if I write it this way, right? So the y values are inside, so this should be dy, and this should be dx. This is really important, okay? So like that. If you flip them, it's not, if you flip only the limits of integration or only the dx, dy, you will mess everything up, okay? Or I could write it this way. 1 to 2, 0 to 2, x minus 3y squared, dx, dy, okay? So the x are here, the y are here. This is important, okay? Now, you look at those two integrals, and they look both easy. So you just pick one, and that's fine, right? So I'll do this one. But in the next example, you'll see that you can make a smart choice, okay? So let's do that. All right, so I'm going to compute this iterated integral. Okay, again, always inside part first, right? So the inside part is an integral with respect to y, so x is fixed, right? So I'll just write the outside part, that's just there for the right. So I'm integrating inside with respect to y, okay? So the integral is what? xy minus 3y cubed over 3 between 1 and 2, right? So this is the inside part. Yeah? Is that okay? All right, so I'll evaluate that. Integral 0 to 2. So this will be x times 2 minus 3 times 2 cubed over 3 minus x times 1 minus 3 times 1 cubed over 3 dx. Okay? So let's just clean that up. So this is 2x minus 8 minus x plus 1. If you see me make a mistake, just let me know. And so this is the integral 0 to 2 of x minus 7. I hope I didn't mess up. Okay. Okay, and then this is easy. This is just x squared over 2 minus 7x between 0 and 1. And that's 1/2 minus 7. Something's fishy here. Oh, sorry, 0 to 2. Yes, thanks. Minus 7 times 2. Not 1/2. And that's 2 minus 14, which is minus 12. If you're wondering why I'm getting a negative, it just means that this function is going below the xy plane when you consider over this rectangle. That's all it means, right? So we are getting more negative stuff. That's all that means, okay? Now, I could have done the second iterated integral. I would get the same thing, obviously, okay? So let me do one where the flavor is really different, and I'll finish with this, okay? So here's a last example for today. So we're asked to compute the following double integral. It's the integral of y sine of xy over the rectangle 1, 2 times 0, pi. Okay, so again, this function y times sine of xy is super nice. Fubini applies. So use Fubini, right? So this is equal to either the integral from 1 to 2, integral 0 to pi of y sine of xy. So again, be careful. 0 to pi is the y values, so dy here dx, or integral 0 to pi, integral 1 to 2, y sine of xy, dx dy. Okay. But now if you look at those two iterated integrals, one of them looks a bit more interesting than the other. So let's take a look at this. So you always start on the inside, right? So let's take a look at this inside part here. I have to integrate with respect to y. I have to integrate y times sine of xy. If you remember a little bit your integration, that looks like a job for integration by parts. Okay, that's what you need to use. Well, that's not so bad, but can we do better than that? Well, if you look at the inside part of the second guy, you're integrating with respect to x. So y is a constant. So that y that multiplies the sign is not a problem. So that's actually just a straightforward integration. Well, that's not very readable. Let's try that again. Now, there's no guarantee that on the second iteration, you're not going to get into more trouble on the second one. But at least since you don't know where this is going, you might as well use the second one. So we compute easier. Okay, so I'm going to do this one. Okay. Okay, so let's see. So the inside part is an integral with respect to x, right? Y is a constant. And so if you remember, derivative of cos is minus sine. So that should be minus cos of xy. Let's think about it. If I differentiate, you can do a substitution if you prefer. Just write it out. Okay? But the derivative of cos is minus sine. With the chain rule, I'm going to get a factor of y because it's a constant. So I get exactly what I want. So this is the integral. This is the outside integral, which I haven't touched yet, right? This is minus cos of xy between 1 and 2. This is dy. So I've just computed an antiderivative for the inside integral. So this is integral 0 to pi. I evaluate that this is minus cos of 2y plus cos of y. So far, so good. Okay. And so I'm left with this integral with respect to y, which is, again, straightforward. So I'm very happy. I know I chose the right integral. So let's integrate this. So derivative of sine is cos. So minus sine of 2y, but I need a 1/2 there to compensate for the chain rule, right? Plus sine of y, and this is between 0 and pi. Okay, and so I evaluate. Sine of 2 pi is 0. Sine of pi is 0. Sine of 0. So everything collapses. It's just 0.
Shouldn't we divide by x in the above equation?
Here?
Yes.
Well, no. So I'm integrating with respect to x, right? So take the derivative of this. If I take the derivative of this, I should be getting this because I have the factor y already. So I don't.
Okay, yes.
Yeah, you see?
Thank you.
Good. Okay. So this illustrates that, so sometimes, so the moral of this example is sometimes one direction. If you look in the book, they actually do the computation for the first integral that I wrote down, You get integration by parts first, and then the second one is complicated too. So it's way more complicated to do the first one. The one direction is much easier than the other.
Sir,
Yep.
I don't really understand when Fubini's theorem does not apply, or we cannot use it.
Okay. You'll never see those. It can happen. Okay, so that extra technical thing is that the slice functions have to be integrable. You can cook up some functions that are integrable over the rectangle, but when you slice, the slices aren't, but it's just like they're super nasty functions.
Okay, so that's the same as the zero thing that we were doing before, right?
Be more precise.
Like we were doing like before that, the definition an area set as that is bigger than zero, or an area that is too small.
Oh, the measure zero thing. Yeah.
Yeah.
So this is good for us. I mean, yeah, I know it's not like super clear right now, but okay, let me just quick introduction. Okay. So preview of next class. To sort of try to illustrate that thing. So now we know how to integrate a function over a rectangle which is parallel to the coordinate axes. But that's not going to get us very far, okay? So how do you integrate over a more general region? So here's the trick, okay? So to integrate over more general regions. And it's just a picture, basically. So suppose that the region is, let's say something like that. Okay, I want to integrate over something like that. Okay, so my function is defined over something like this. So there's a graph like that, and I want to basically, right, find the volume of the solid under the graph of my function over this region. So what can I do? Well, the trick is this. You draw a rectangle around this region. So you have your region like that, and you draw a rectangle which is parallel to the coordinate axes. Okay? Now, you want the right function to get the right volume. So what do? Is above this thing, it'll be the original function, right? This one. And on the rest of the rectangle, you don't want this to count. So what are you going to do? You're going to define the function to be 0. Now that's a nasty looking function, right? Because it's not continuous. There's like this big jump, right? But the jump is on a curve. If your region has a nice boundary, you see that this function is continuous everywhere except on the boundary of your region, which is of measure 0. So Fubini's theorem will still work. That's why I needed to mention that. Okay. Now,
Right.
this is the trick to be able to integrate over more complicated regions. We're going to exploit that and see some techniques to integrate over regions which are not rectangles. Hopefully that's so. F, the new function is continuous. Oh yeah. I have no idea what's going on. Continuous on R, rectangle, except on boundary curve, which is okay. So Fubini will work. Okay, so that's why I needed to mention that earlier. Okay,
All right.
but I'll do that next time. Are there any questions, comments? That's good. Okay, so if not, that's it for today, and I'll see you tomorrow. Okay, excellent. Don't forget the web works. And if you have questions, don't hesitate. Buenas noches.